Here today we have an interesting topic, a session this afternoon, Inertial Measurement Units. Now this webinar, will be recorded. You'll be muted in the meantime, but ask your questions in the chat box on the right-hand side. The webinar will last about half an hour, and thereafter you'll get the chance of about 15 minutes to ask your questions. We have two interesting speakers here. Our specialists is Mehta and Kevin Jos, who are ready and waiting for the presentation. And without further ado, most welcome to all of you. Let's see what Nenad has to say. Over to you, Nenad.
Thank you, Manfred. So, hello and warm welcome from my side as well. I'm Nenad Mehta. I'm product manager for sensors at Electronic, and with me is...
And my name is Kevin Jos. I'm also a product manager with Electronic. Today we will be talking about IMUs, which is a small sensor system with a wide range of applications.
So let's begin. Let's have a look at the agenda. We are going to talk about IMUs, which stands for Inertial Measurement Unit. What are they? Then we are going to talk about the acceleration sensors and gyroscopes. How do they work? On which technologies they work? Their working principle. And then we are going to have a look about the applications and use cases where these sensors could be used. In the end, we will also introduce to the motion sensor portfolio from the Electronic ISOs. And in the end, we will conclude the presentation with some added values that we offer. So moving ahead, IMUs. What does IMU mean? What do IMU mean? Basically, it's an abbreviation for Inertial Measurement Unit. And you might think that what do an IMU do, or how can I see and where can the IMUs are used? Basically, the IMU are a sensor system which detect and measure their own movement in a 3D space. And you might have encountered some of these kind of sensors in your day-to-day life. Kevin, do you know any of these sensors where you use in day-to-day life?
So IMU can be found in most of the daily life applications that we use. So for examples, if you look onto smartphones, tablets, wearables, hearables, everywhere you can find these IMU units inside. One interesting application would be like if you are using a mobile, you might have observed if you change from a portrait orientation to a landscape orientation, the mobile phone is able to detect it. It's also based on this IMU sensor, and there are a lot of applications, I would say, in which are like very common for people in daily lives where IMU is used.
Yeah, kind of a TV remote or even a joystick for your PlayStation, where you move your joystick and then
exactly
the information is also recorded or seen on your car moves also left or right or even faster or slower. Yeah, I think we see
almost everywhere.
Yeah, we see them almost everywhere, these kind of sensors. But not just that, they are also usually present in some complex hardwares like drones or aeroplanes or rockets, where they are used to stabilize in the air or locate their positions in the air. So you might think that the applications of this kind of sensor last from very simple applications to complex hardware, but I can assure you it's not so complex to understand when we go into deeper that what IMUs are made of. So going ahead, what IMUs are made of. So basically IMUs consist of an accelerometer, a gyroscope, or a magnetometer, or all three of them basically. So when we look at just an accelerometer, so accelerometer consists of 3 measurement axes or 3 TOF or degrees of freedom, so as to say. So this can measure the linear change in the velocity, so as to say. This can also be combined with 3 more axes. So you have 3 axes that you can measure, and then you can also measure 3 more axes which are rotating. So 3 more axes that you can measure, and in total, then you can have 3 plus 3, 6 degrees of freedom, or 6 measurable axes. Mm-hmm. And these are called like 6 axis IMUs. And then you can add also a magnetometer, which uses the magnetic field of Earth to measure the directions. And you can have 9 measurement axes in the end. So in generally saying, so the IMU can consist either 6 measurement axis, or it can also in some cases consist 9 measurement axis.
But Nenad, what do you mean by degrees of freedom?
Yeah, I think I'm going to show you what do I mean degrees of freedom in the next slide. So let's move on to the next slide, with which we can maybe explain each three concepts of acceleration sensor, the gyroscope, and the magnetometer. So let's take a plane and then let's take a basketball. So basketball can move in one plane, so left to right, front and in the back, and up and down. So basically these are the 3 degrees of freedom of movement or linear movement. And this gives us 3 axes of measurement. So you can measure these 3 things. Now in the same plane, the ball can also rotate on its axis, forward or backwards, or left to right, or on the sides. And this gives us 3 more degrees of freedoms of rotation. Okay. So when you add these 3 degrees of freedoms of rotation on top of the linear movement, you have the 3 axes which are stationary, so as to say, and they all can rotate on their own axis. So you can now just not measure the movement, but also with the movement, you can additionally also track the rotation of an object. And now on top of that, if we add also the Earth's magnetic field, so the direction, so 3 axes of direction, north, south, east, west, up and down, then you can also track the position of an object relative to the Earth's magnetic field. So in the Earth, you can also track where the object is located relatively. And this gives us 9 axes that we can measure. So in the end, we are just first measuring the linear movement, then the rotation, and then the relative position. So we are just making our application or 6 measurement axes more accurate by adding a relative accuracy through a magnetometer or through an magnetic axis. So what I want to say in the end is, the more axes that we can measure, the more accurate orientation of an object we can detect in a 3D space. Now we have seen this basically how the physical quantities are being measured, and now we can check in the next slides how, based on this, accelerometer and gyroscopes will work. For this webinar, we are not going to focus on the magnetometer. So let's go ahead and see how accelerometer and gyroscope works. Kevin.
So let's start from the basics. What is acceleration and accelerometer? So acceleration can be said as the rate of change of velocity, or also as the second derivative of displacement, because velocity is the rate of change in displacement. Usually acceleration is measured in meter per second square, which is the standard index unit of acceleration. So this is a vector quantity which can be either positive, negative, or 0 based on the direction of the acceleration. So the sensor used to measure acceleration, that's called accelerometer. So usually these kind of sensors measure acceleration in a particular axis, and in some special cases, it's capable of measuring acceleration in multiple axes also. So even though the SI unit, the standard index unit of acceleration, is meter per second square, sometimes these kind of sensors measure acceleration in gravitational units like G or milli-G. So we will be seeing G and milli-G further in the slides and the presentation, and don't confuse it with some other things. It's the acceleration due to gravity, which is 9.81 meter per second square. So if you are moving on to the next slide, which is what are gyroscopes? Gyroscopes are the sensors that are used to measure angular rotation or angular velocity. Just like accelerometers, these sensors measure angular rotation along a particular axis, and in some cases they are capable of measuring angular rotation in multiple axes also. There are several units for measuring angular rotation. Mainly, most of them are familiar with RPMs and also radians per second, but most of the gyroscopes use degrees per seconds to measure angular rotation. The 3 main types of rotations are roll, pitch, and yaw. So roll is the rotation of an object along its x-axis, pitch is the rotation of an object along its y-axis, and yaw is the rotation of the object along its z-axis. We can see that there are a lot of technologies in gyroscopes, like mechanical gyroscopes, fiber optic gyroscopes, also ring laser gyroscopes. And among these kind of different technologies, the most prominent and popular one are the MEMS technology. And let's see more about the MEMS technologies in the upcoming slide.
Yeah, good that you asked about this MEMS technology. This was a keyword also I was looking for. What does MEMS technology stands for? You talked about different types of sensors that different type of technology that the sensor is made of, and one of the most popular one is MEMS. So MEMS stands for Micro-Electro-Mechanical-Systems. Basically, name says it all, or there's another abbreviation. So it has a mechanical system, which is a moving part. So this is the part where some movement is happening, and after the movement, the mechanical movement is converted into the electronic part. So this is computed by an electronic system. So these both systems are combined in one single package, and that's how the single package, and they are scaled down to a certain very small, a very tiny level, and that's how you get a MEMS-based technology to work. So basically, what do we achieve by downscaling the whole system is that you get faster measurement time, because the system becomes very sensitive, because a very small change in mechanically you can also detect and compute electronically, so that you can measure a very small amount of change. The MEMS technology also enables to have better processes and scalable processes, so that you can produce this type of sensors in mass production, which also in the end is very cost effective.
So Ninad, I have a question. I see that the abbreviation MEMS stands for Micro-Electro-Mechanical-Systems.
Mm-hmm.
How small are these structures?
Oh, really? I can show you a picture next to it. So here you see a picture. Can you imagine what is it? On the background, I can say that's a MEMS structure. So it's a mechanical structure which is moving. Mm-hmm. But on the foreground, the big thing is a hair.
Wow.
A human hair. So basically you can see how small these structures are.
That's very tiny.
Usually they are 100 times smaller than a human hair, around ranges from hundreds of nanometers to around 300s of micrometers. So you can imagine how small they are and how small changes they can detect as well when they move, mechanically move. Yeah. So this is a big advantage of MEMS technology, that gives us very sensitive sensors to be used in our applications. Now we have seen the basics of the MEMS technology, how they work. Let's have a look how the MEMS-based acceleration sensor and how MEMS-based gyroscope would work and would look like.
So let's look on to the working principle of MEMS accelerometer. So this can be you can see the animation here. This is a visual representation of the internal working of MEMS accelerometer. So the gray parts are the movable or the fixed plates, which does not move at all and are fixed to the housing of the sensor. And the blue part is the light blue part is the suspended proof mass, or it can be also called as the seismic mass. It also consists of the movable electrodes attached to it, and these electrodes move whenever the sensor experiences an acceleration. And this proof mass is suspended to the housing of the sensor using polysilicon springs, which are shown as the dark blue objects. And whenever there is an acceleration experienced by the object, the sensor will, inside the sensor, these movable plates will get displaced a little bit based on the magnitude of the acceleration. And this will cause a change in displacement between the electrodes, like the fixed electrode and the movable electrode, which will in turn results in a change in the capacitance. We know the capacitance is inversely proportional to the displacement. So this change in capacitance is converted to an analog signal using special circuitry. And then this analog signal is converted to a digital signal using analog to digital converter, and which can be, and the digital value can be taken out by the user using a microcontroller from the sensor. So this is how the MEMS accelerometer works. Let's look on to the working principle of MEMS gyroscope. So MEMS gyroscope and MEMS accelerometer have something in common, which is a proof mass. So in this case, there are three main units. One is the proof mass, which is always which is like freely suspended using polysilicon springs, as we have seen before. And also there is like this proof mass is kept oscillated in this. For if you are looking onto this example, this proof mass is always oscillated in the x-axis direction with the help of an oscillation or driving system. And also there is a sensing system which is there to detect the change in capacitance. So I'll explain in detail. So if you are looking onto this example, you can see that the z-axis is pointing outwards from the screen. So whenever there is a angular rotation along the z-axis, then the proof mass will get a Coriolis force, which is caused by the Coriolis effect. It will get displaced in the y-axis, and this will cause a change in capacitance. So it works almost similar like the accelerometer, and this change in capacitance is converted to analog voltage and then later into digital signal. So this is more like another visual representation of how the MEMS gyroscope works internally. A special configuration called the tuning fork configuration is used in our MEMS gyroscope to make sure that the sensor's operation is independent of linear acceleration. So if there is an external acceleration, it makes sure that like the proof mass can get displaced, and it can get wrongly identified as a angular rotation by the sensor. To prevent this, the tuning fork configuration is used to make sure that the sensor is only picking up the angular rotations. So maybe we can look on to some applications of this kind of sensors. So the first application is the tilt detection. We have seen that accelerometers are capable of measuring acceleration. But there's one more thing that the accelerometer can measure, which is the tilt. So if you are looking onto an application using solar trackers, it needs to be properly aligned with the sun every time to maximize energy harvesting. So in this example, the solar tracker is properly aligned to the sun in the morning, but in the case of noon and evening, it's not properly aligned. So this is like inefficient, and it reduces the the power that can be obtained from the sun. So if you look on to the next slide, we can see that in this configuration, if the solar tracker is capable to move according to the sun, then we can maximize the energy harvesting. So this is much efficient approach rather than the previous one. So in this kind of application, it's important to measure the inclination so that we can make sure that the solar tracker is properly aligned with the sun. So in this case, accelerometers are used. So let's look on how do these accelerometers measure inclination. So accelerometers at rest, they only measure the acceleration due to gravity. So ideally, if you place a accelerometer sensor in the table or in a horizontal place, it should measure 0 millig, 0 millig, and 1000 millig. And this 1000 millig is caused by the acceleration due to gravity. So if you are looking onto a different configuration, which can be, if you see in this configuration, you can see that the acceleration due to gravity is completely acting along the x-axis and y-axis. And if you resolve this acceleration due to gravity in the x-axis and y-axis, you will get two equations. And from these equations, you can easily calculate the theta associated with which is the angle at which the sensor is inclined to the ground. So this is how an accelerometer measures inclination, and this is used in a lot of applications. So accelerometer is not just a device that can be used to measure acceleration, but it can be also used for measuring physical quantities like tilt, which is really interesting. So as we have seen here, accelerometers can be used to measure tilt only for stationary objects. But for example, the solar tracker doesn't move, and it can be used to measure the inclination in that case. But what is the case if the object is moving? Do you know how do they measure inclination for a moving object?
Yeah, that's a good question, because it's difficult for the acceleration sensor to measure the tilt when the object is already moving. So we saw that we can measure a tilt for a stationary object. Let's have a look at this example where you have a stationary object, and when the object is being tilted, the acceleration sensor can already detect it. So there is a tilt happening, and it is acceleration sensor is detecting. But let's consider this plate is already moving in certain direction. What would happen then? And then in that direction, the tilt would also happen. So there are two physical phenomena are happening, that the plate is in a movement and also being tilted. So acceleration sensor will detect these both movements. So basically, the acceleration sensor will respond to the both movements, but as a user, we cannot identify if the response was due to a tilt or it was due to a motion, because the acceleration sensor can detect both and it can also react to both. So this won't work. This cannot be resolved just by using an acceleration sensor. This can be resolved by using a gyroscope, which can also measure multiple axes simultaneously when they are in rotation, which acceleration sensor cannot do. So let's take an example of a moving object that moves alongside and rotates around its axis, and then the gyroscope output will also depend based on the rotation of the object, even though it is moving. So depending on which direction the object moves, the response will change. In this example, the response of the z-axis of the gyroscopes. Okay. So in the end, what we can do is, in such kind of applications where the objects are constantly moving and rotating, for example, like automated guided vehicles or robotic arms or robots, you can combine the response from the acceleration sensor and the gyroscope together to have the rotation and the movement of the objects and get a clear idea about how they are being moved in the 3D space, so as to say. So basically, gyroscope only responds to the angular rate of change about each of the axes, and it won't respond to the linear motion. On the other hand, through an accelerometer, you can detect the linear motion. So basically, by combining these two sensors together, you can already get even more information when the object is in motion. We saw now that what we can do with acceleration sensor and gyroscope together. Let's take another example of asset tracking and indoor positioning. So asset tracking is one of the most important industrial application for supply chain. Even during the pandemic time, we saw more than 150 millions of containers being shipped, because we need to make sure to have a better overview about the supply chain. We need to track our goods that we send, to check for any sensing impacts, the sensing impacts for the damages, or even to track our shipments out, containers movements very accurately.
So, Nina, what I felt was like, my thought was like, genus was the sensor used to measure to locate an object. But how do IMUs or accelerometers help in this case?
Yeah, you're right. I mean, GNSS is sufficient also to locate your object. But let's say take an example. If you're moving in a container from point A to point B and it passes through a tunnel where the GNSS reception is not possible, so you need to have more sensor input in order to track the container. So for example, with the GNSS, you will have a straight line, which is not an accurate positioning of your container, so as to say. But with an IMU combined with the GNSS, you can still locate the relative position of your container when the GNSS signal is not sufficient. So basically, you can combine the GNSS data and acceleration sensor or gyroscope data together to get even more accurate positioning of your sensor. And this can be also used in indoor warehouses or production lines where the for example, you want to locate position of a forklift, so as to say. Next, moving ahead, we can have a look at some of the more applications. For example, the GNSS, for example, the 3-axis or 6-axis gyroscopes can be used also for predictive maintenance in, for example, as for medical milling machines. For that, you need to also have to track 6D orientation, or even do a predictive maintenance or the vibration checking of such kind of milling machines, so that you cannot have a downtime. Another example is intelligent housekeeping devices or smart robots, where you need to have a real-time monitoring of the robot and which orientation or which direction they are moving. And usually they are also battery operated for some times.
Yeah. So if you're looking into gym equipments, you can see that tracking the motion of the equipment is very important. It makes sure that you are not moving the equipment in a wrong position, which might cause some injury, or like it's more ineffective. So to make sure that the motion is effective, it's important that you have an IMU sensor in this kind of equipments. Also, if in the case of an accident, it can be used to detect like maybe like a free fall of the equipment to alert people if something goes wrong with the one who is exercising. So you can see this kind of sensors in smart sport equipments, which are capable of detecting the motions of the equipment and analyze the exercise properly.
Okay. Kevin, now we have seen a lot of applications. What type of sensors or what type of sensor can we offer in order to fulfill these type of needs?
So the motion sensor portfolio of the Burt Electronic has two sensors. The first one is the 3-axis acceleration sensor, also known as the WSC and ITDS. This sensor is based on the MEMS capacitive sensing principle, which we have mentioned in the previous slides. So this sensor can measure acceleration in X, Y, and Z axis. And there comes the 3-axis from the 3 axes. So the sensor is capable of outputting data at a resolution of 14 bits. So the analog to digital converter is 14-bit, and hence comes the digital resolution of the sensor. As we have seen, this sensor is based on MEMS capacitive sensing principle, and hence it has a small size. So the maximum dimension of this sensor is 2 millimeter, which is very, very, very small. And also the sensor is capable of interacting with a microcontroller with I2C and SPI communication protocol. And also there are 2 different interrupt pins associated with the sensor. Like if you have some special activity to be detected, then the sensor can detect it, and then it can create an interrupt using these interrupt pins and inform the microcontroller that a special event had occurred. The sensor is intended to operate in a temperature range between -40 degrees Celsius to 85 degrees Celsius. So this is our sensors are more focused for industrial applications, and hence comes this operating temperature range. So the next sensor in our product portfolio is the 6-axis IMU, which is a combination of accelerometer and gyroscope, which is also known as the WSC and ISDS. Just like the other sensor, this sensor is also based on the MEMS capacitive sensing, and it can measure acceleration in 3 axes, X, Y, and Z, and also it's capable of measuring angular rotation along this X, Y, and Z axis using the gyroscope. So it's like 3-axis accelerometer and a 3-axis gyroscope combined in a single package. So the digital resolution of this sensor is 16-bit. For the ITDS, we have seen that the digital resolution is 14-bit, and this is more upgraded version, which has like a 16-bit digital output, which further increases the sensitivity of the sensor. Also, the sensor has a small size, which is like, so the maximum dimension of the sensor is 3 millimeter. Even though there are 2 sensors in this small package, still it's 3 millimeters, which is like, I would say, very good. Just like ITDS, ISDS also has a 2 programmable interrupt pins, and also I2C and SPI communication interface to communicate with the microcontroller. It's also capable of storing acceleration values using FIFO memory. So FIFO stands for first in, first out. It's the memory system that the sensor has. So if this sensor can be operated at a high output data rate. So sometimes the microcontroller won't be able to fetch data from the sensor every time, or maybe the microcontroller is overloaded with some other task. Then these data can be stored in the FIFO, and whenever microcontroller finds time to get this data, it can come into the FIFO and take all the data together and analyze this data. Also, this sensor is operated in a temperature range between -40 to 85, since we are intending the sensor for industrial applications. Now let's look onto the block diagram of this sensor. So the block diagram of ITDS and ISDS is almost similar, apart from the part that ISDS has both acceleration and gyroscope inside. So the MEMS element detects this change in acceleration, like the acceleration values. It measures the acceleration value and also the rotation values. And these values are converted into analog signals using special circuitries. And this is converted later into the digital signals using analog to digital converter and are stored in the registers of the sensor. So after storing these values in the register, either the user can take out these values from the register using I2C or SPI communication, or it can also perform some embedded functions. Like in this case, the ISDS and ITDS is capable of detecting free falls, tab detection, orientation, wake up, stationary motion, and also activity and inactivity. So these functions are already embedded inside the sensor.
So you mean to say that I can use and benefit from this functionality so that I can, when I connect my sensor to a microcontroller, my microcontroller can be in sleep mode.
Yeah.
The sensor can perform its duty with the inbuilt functionalities, for example, a free fall tap detection, so that the microcontroller doesn't have to ask for the data from the sensor on some certain time period. So sensor will compute these things on its own, and then whenever some event is occurred, then the sensor will put out the data to microcontroller, and the microcontroller will be awakened.
As you have said, like the microcontroller can stay in idle state, just like you said, and it can reduce power consumption to a lot. And also this is an efficient method of like communicating. Like whenever the microcontroller doesn't need to always take out the data from the sensor. Whenever there is a special event occurred, then the microcontroller can take this data and analyze it. So this is more like efficient and also reduces power consumption.
This can be used for many of the applications that we showed before, and they can be also benefit on this kind of built functionalities from the sensors.
Exactly.
Then this brings us to the end of the presentation. Before we conclude the presentation, we want to also show what we offer in order to accelerate your project or prototyping. We offer the sensor evaluation boards for each individual sensors, or also via sensor featherwing, where multiple sensors of us is mounted all together. We also offer a hardware platform so that you can connect the sensor evaluation boards to a microcontroller of your choice. Then we also have the CAD layouts so that you can do a faster prototyping. And then we also offer the application notes and software development kits where you can directly use your software or as software example codes from us and take the sensor into operation from your own.
So as a summary, you have sensor boards to evaluate the performance of the sensor, which includes the evaluation boards also. And there's a hardware platform which can be used to connect these evaluation boards to a microcontroller easily. And also you have hardware design so that you can start working with the sensor projects or with the prototypes easily before even receiving the sensor. And also there are software examples in the software development kit, so that you can start start with the developing as soon as you get the sensor with this software development kit.
So thank you very much. That is the end of the presentation. Thank you very much for listening and paying attention. And now we are ready for the questions. If you have any questions, please let us know. Thank you.
Thank you.
Yes, gentlemen, Nenad and Kevin, thank you very much for a very interesting presentation. In the meantime, we actually had some questions here as well in the chat forum, and I'd quickly like to address one or two of them. What would happen if I operate outside the temperature range which you mentioned from -40 to 85? If I go above 85, what happens?
So for both the sensors, ISDS and ITDS, the absolute maximum rating of the temperature is 125 degrees Celsius, which means if you operate the sensor above 125 degrees Celsius, then it can go into failure. So if you are operating the sensor above 85 degrees Celsius, it means that the acceleration values or the gyroscope values that you obtain from the sensor are not very reliable. So it's intended to operate in the temperature range between -40 and 85. If you operate it above 85, then it can be the data that you obtain from the sensor is not reliable at all. And also if it goes above 125 degrees Celsius, then chances are high that it might fail.
Okay, well, thank you. One more question here. Is sensitivity increased if I use the smallest full scale, in this case 2Gs?
Okay, so both our sensors have a full scale up to 16G, from 2G to 16G. So if you are using the 2G, then you can achieve more sensitivity. Like sensitivity and full scale are quite interlinked. For example, if you are using 16G, then you are having an advantage of measuring high accelerations of a high magnitude up to 16G, but it comes at the cost that the sensitivity is reduced. So if you are using 2G, then you are having much more sensitivity. You can detect small changes in acceleration, but the problem is like if you have an acceleration of about 2G, then the sensor won't be able to pick up this acceleration. So yeah, sensitivity is increased with decrease in full scale.
Okay, interesting. Yes, thank you. One short question. Are there any tips to reduce power even further, the power consumption?
I think we just talk about this topic, that how can you reduce power, because we have, with the sensors, there are built-in functionalities. So the microcontroller usually is not in the active mode and it is in the sleep mode. And by that time you can the sensor can do its own work, and then you can use this to your advantage, and the overall power consumption can be made as low as possible.
Yes, okay, thank you. We still have a bit of time here. One more question here. Does the mechanical resonance of the accelerometer spring mass system affect the overall sensor frequency response? I hope you understand that one.
Yeah. So the sensors that we have, it also has a resonant frequency. So usually these kind of resonant frequencies are always above the bandwidth of the sensor. So for example, if you're looking onto ITDS, it has a bandwidth of 400 Hertz. And the resonance frequency for the ITDS is much above 400 Hertz. So if you're using an application, if you're using the sensor for an application which is like above 400 Hertz, then ITDS is not suitable for that. Or if you're looking into ISDS, then it has a bandwidth of 1.5 kilohertz. And this resonance frequency is much higher than that. So if the point is like you won't be using a sensor like if you're having a high frequency than 1.5 kilohertz, then ISDS is not suitable for this product. Then the resonance frequency is not an issue in this case.
Here's a question, quick and easy. What is the typical lifetime of an IMU? I assume more than sufficient.
Of course, I think we give also a long life availability of the sensors, so they are available for at least 10 years. And the typical lifetime, for sure, there is a drawback of this MEMS-based acceleration and gyroscope sensor that they intend to have some drifts, but we do also in our labs some long-term acceleration and qualification tests by which we can also obtain some drift values, that how the drift will be looking in the next 10 years or next 5 years, and that you can also take into account when you are using it in application. But this is something that is seen in this kind of technology. Usually for the drift reduction, 3 more axes of magnetometer are used, so that you have in the longer run less drift and or a compensation of this drift and more accurate data.
Yes, one more question here. Does WIRT have a 9 degrees freedom IMU in plan? Is there anything planned in the future portfolio?
So if you look onto 9-axis IMUs, it's mostly used in consumer applications. So we are mainly into industrial application. That's the reason why we are started with 3-axis and 6-axis IMU. But it doesn't mean that we will not have 9-axis IMU. If maybe there's still a chance that we might have 9-axis IMU in the future in our product portfolio.
Yes, okay, lovely. There's one more question I see there. Is it possible to get the slides of the webinar? Yes, I believe they will be shared, they will be made available. And I see that our technical support is doing it right now. Yeah, it's running. I have one more question out of my own thought here. And if I have a 6-axis accelerometer, what accuracy can I get if I go well beyond the physical limits of the actual sensor? Do I break the sensor, or does it recover back to its normal operation?
Depends how harsh the conditions are. Basically, we do check them for the harsh conditions during our qualifications. But at some extent, for example, if you are measuring up to 16G, then it will cap up to 16G because of the limitations of the A to D conversion. So you will get maximum of 16G. But physically, this might harm the sensor for longer term if you expose to harsh conditions for a longer period of time. It could also induce some long-term inaccuracies once it's also back in the defined measurement range. But this is something that we do not recommend to do.
Also, I would encourage you to look onto the data sheets that we have, where we have clearly mentioned that the absolute maximum rating of the sensor, like the temperature and the highest shock that the sensor can survive and things like that. So it would be interesting if you go and look onto the data sheet.
Yeah, okay. Thanks a lot there. I see there's one more here. Are there any, or is there any possibility to get customized solutions? Would there be a need for customized solutions?
I don't fully understand in what direction we want to customize this. So, but if you have any questions, then please write us to the email address wcs@we-online.com and maybe share your requirements. Then we can get in touch with the R&D team, engineering team, and then we can see if we can do something out of it or not.
Okay, well, thanks. And I see there's one more interesting question here. I have a 12-bit A to D converter. Can I use a 14-bit 3D IC also with less resolution? Well, I think the last 2 bits could also be ignored.
Yep.
Yes?
Yeah.
Okay. And then we have a last question here. Will there be an integrated sensor system?
Maybe, Mantha, just to the previous question.
Sure.
The sensors that we have are already giving you a digital output. So you don't need to have one more ADC after the digital output. So basically just to make the thing then more first amplified and then through the filters, passing through the filters, converted through an ADC, so in digital form, and then you read it up. So basically,
okay, you had it in the slide previously that the digital output is 14 bits wide?
For 3 axis and for 6 axis,
16 bits.
16 bits. Okay, lovely. Thank you. Yeah, will there be an integrated sensor system that includes all the orientation and orientation calculations on the sensor to unload this algorithmic form from the microcontroller? Do I understand that correct? To unload this algorithm?
So what I mean is like what I understood from this is like will there be a system where the sensor fusion happens inside the sensor? So usually this orientation and rotation calculations are usually done using complex algorithms like Kalman filters and Magwick filters like that. So they usually combine this kind of gyroscope data and the accelerometer data together using some complex algorithms. So if you're looking onto sensor, it doesn't have that much computation capability. It's capable of some functionalities like free fall and wake up, but it's not capable of doing some complex functionalities like Kalman filter or sensor fusion. So for this purpose, you would definitely need a microcontroller. So it's, I would say at the, considering the technology that we have now, it's like impossible to have this kind of algorithms inside the sensor.
Yeah,
maybe in the future.
But maybe in the future you can include the better processing power and then edge computing.
Yeah.
With the edge computing, you can have these capabilities on the chip.
Exactly. And in the future, I think it would be possible.
Right now, we don't support this.
Yeah.
One last question. What does the self-test in the sensor actually involve or entail? What is the purpose of the self-test function?
It's almost like calibrating the sensor.
Okay.
For maybe so for example, it's just a test that can be used by the user to make sure that the sensor is working properly. So it will create an internal acceleration inside. And if you're receiving the exact acceleration values and output from the accelerometer, then you can understand that the sensor is working properly. So this is like a internal test to make sure that everything is working properly with the sensor. And this kind of self-test is available with ISDS and ITDS.
Yeah. Okay, well, lovely. I think we've summarized this and our time is just about up as well. Kevin and Nina, thank you very much. Hope to see you again soon for next presentation. And with that, I think at this stage, we can actually then call it a day. And from my side, have a good day. I hope you had some good information to work with. And, well, if you have any questions, write us a ticket. We'll always be available to answer any questions. Gentlemen, thank you very much and have a good day.
Thank you.
Thank
Bye-bye.
you. Bye-bye.